Hello everyone, we are Group 11. Our teams include Lolo Kun and Lam Ting Wei. Our project title is Bayesian Logistic Regression with Low-Rank Interaction Matrix, a comparison of sampling and variational methods. Let's start by talking about the problem statement. We want to perform Bayesian inference for a logistic regression model with a low-rank matrix defined as follows. However, it poses challenges of intractable posterior due to nonlinear likelihood functions and low-rank structure. Hence, we try to implement and compare two methods for posterior approximation: Hamilton Monte Carlo (HMC) and variational inference (VI). This is the model specification, where the prior and posterior are as follows. First, let's discuss about Hamiltonian Monte Carlo, or HMC, and advanced MCMC method. HMC leverages Hamiltonian dynamics to effectively sample from complex posterior distributions by modeling the negative sloped posterior as potential energy and introducing kinetic energy through momentum variables. The log posterior combines the log likelihood and prior as below. We implement HMC with leapfrog steps to simulate dynamics, updating U and beta based on gradients of the log posterior, where Hamiltonian dynamics and leapfrog steps as follows. To ensure efficient sampling, we adaptively tune the step size epsilon during our 1,500 iteration warm-up phase using dual averaging, targeting an acceptance probability of 0.65. The algorithm runs for 3,000 iterations, with trajectory lengths randomized between 3 and 9 steps. Posterior samples are obtained after warm-up, and prediction uses the posterior mean. Next, we have variational inference, or VI, which approximates the posterior by optimizing a simpler distribution. We use a mean field variational family, parameterized by means and variance. The goal is to maximize the affordance lower bound, or elbow, which balance the expected log likelihood and KL divergences between the variational and prior distributions. Using the reparameterization trick, we sample U and beta to estimate the elbow with 100 Monte Carlo samples. Gradients are computed automatically with JAX, and we optimize using the Adam algorithm from Optest with a learning rate of 0.005 over 5,000 iterations. For our experiments, we generated 3 synthetic datasets, each with 1,000 samples, 100 features, and a binary target. We use trinket split, which split into 80% training and 20% testing. The ideal dataset adheres to the model's low-rank interpretation with rank k equals to 2, no noise, and balanced classes. The noisy with imbalanced dataset includes Gaussian noise with a standard deviation of 0.5 and reduce positive labels to create imbalance. The higher rank dataset uses a rank 10 interaction matrix to test robustness to rank misclassification with no noise or class imbalance. Both HMC and VI were implemented in Python using JAX on a 2023 14-inch MacBook Pro with an M2 Pro chip and 60 GB RAM. We evaluate performance using classification accuracy, bias score, log predictive density, and runtime HMC and VI with all 3 datasets. And here are the results. For the ideal dataset, where assumptions hold, HMC hit 96.5% accuracy, just above VI's 96.4%, but VI excelled in probabilistic metric with bias score of 0.028 versus 0.053, and LPD of negative 22.53 versus negative 39.08, while running in 19.59 seconds compared to HMC's 1,328.98 seconds. In the noisy with imbalanced dataset, with the added noise and imbalance, HMC lead with 93% accuracy versus VI's 91.5%, a better bias score and LPD. However, HMC took around 1,368 seconds. For the higher rank dataset, where the model's rank is misspecified, HMC achieved 92.99% accuracy versus VI's 90.5%. However, VI has a better bias score and LPD, with a runtime of around 20 seconds compared to HMC's 1,040 seconds. These results shows that HMC offers superior accuracy and robustness, especially in tough scenarios, but it is computational heavy. This makes HMC suitable for medical diagnostics, where accuracy is the most important. On the other hand, VI is fast, with a significantly lower computational time, making it suitable for resource-constrained or time-sensitive contexts. As we are working with synthetic datasets which limit real-world generalizability, the future work should test with real datasets. We can also explore advanced techniques, such as replacing HMC with no-return sampler, NUTS, and improving 3i with structural variational families or stochastic gradient methods. Lastly, adaptive rank selection for the interaction matrix could enhance model flexibility by tailoring it to the data. This is the end of our presentation. Thank you.